Okay, so for number one, 4 rods being converted into yards. For rods, we're going to put it over 1 to make it a fraction. Rods are going to go on bottom, so they cancel out. Yards on top. 1 rod is 5.5 or 5.5 yards. So the rods cancel out. 4 times 5.5 yards is 22 yards. Excuse me. On bottom, I have to double check this. 1 times 1 is just 1. So 22 yards divided by 1 is just 22 yards. Any questions on that one? Sorry. Number 2, then, we're going from milliliters to liters. If you remember on the metric chart, it goes liters, deciliters, centiliters, and then milliliters. So to get from milliliters to liters, we have to go 3 spots to the left. So our decimal point has to go 3 spots to the left. So that's 0.72 liters. Next, we're going to do some standard to metric and metric to standard. 2.7 gallons into liters. So 2.7 gallons goes over 1. Gallons have to go on bottom and liters on top. 1 gallon is 3. Your textbook used 3.79, so we'll stick with that. So the gallons cancel out. On bottom, it's 1 times 1 is 1. On top, 2.7 times 3.79. Liters, of course, gives us 10.233 liters. So I'm just going to round it to 2 decimal places, 10.23. Number 4, 32 kilograms. Put it over 1. And our conversion factor, kilograms go on bottom, pounds on top. The relationship is 1 kilogram is 2.2 pounds. Kilograms cancel out. 32 times 2.2 is 70.4 pounds. So 70.4 pounds. Any questions on those couple? Okay. 5 and 6 are the tricky ones. Dealing with compound units and rates. For example, number 5 here, that's 10 cubic feet per minute. We're going to use 10 cubic feet over 1 minute. We're going into inches per second. So cubic feet has to be changed into cubic inches. So we're going to do that first. That's going to cancel out the cubic feet. Well, a cubic foot is larger. I'm going to make that 1 cubic foot. Anybody tell me how many cubic inches are in a cubic foot? Remember, 1 cubic foot is 12 inches by 12 inches by 12 inches. It's literally 1 foot by 1 foot by 1 foot. Hence the name cubic foot. 12 inches times 12 inches times 12 inches is 1,728 cubic inches in 1 cubic foot. So 1,728 goes there. We then have to also convert the minutes. We're going to put minutes on top, going into seconds, 60 seconds on bottom. So the minutes cancel out. On top, we have 10 times 1,728 cubic inches times 1. That's 17,280 cubic inches. On bottom, we have 1 times 1 times 60 seconds is 60 seconds. Now we have to divide that out. 17,280 divided by 60 is 288 inches cubed per second. Finally, 5,000 kilograms per meter cubed is 5,000 kilograms over 1 meter cubed. We're just going to convert each unit separately. Kilograms have to become grams. Well, on that little chart, to get from kilograms to grams, we're moving 1, 2, 3 spots to the right. So my decimal point has to move 1, 2, 3 spots to the right. So that becomes 5 million grams for the meters cubed into centimeters cubed. Meters to centimeters is just 2 spots to the right on the chart. However, this is not meters and centimeters, it is meters cubed and centimeters cubed. How does that change things? Well, remember each spot on the chart is multiplying or dividing by 10. If I'm going to the right, it's multiplying by 10. Since it is cubed, it would be 10 by 10 by 10, which is 1,000. And when you multiply or divide by 1,000, the decimal point moves 3 spots. So we move 2 spots on the chart, but each spot on the chart is 3 decimal places since it's cubed. So the decimal point, which is right at the end of the 1, has to go 3 times 2 makes 6 places to the left. That makes that 1 million centimeters cubed. Now we take 5 million divided by 1 million, gives us 5 grams per centimeter cubed. So 5 grams per cubic centimeter doesn't seem like a whole lot, and it isn't. But that comes out to 5,000 kilograms per meter cubed. A meter cubed is a lot of mass. Any questions there? Okay. Well, today we're going to take a look at a couple of new things. The biggest thing we're going to start looking at is angles. So to work with angles, we need some very, very basics of geometry. And I'm going to start you out with the absolute most basic thing in geometry again. That thing right there. It is called a point. And it's merely a location. It is 0-dimensional. 0 dimensions. Everything in geometry, however, is created from that. If I take that point and I pull it in a single direction, I've traced out a line segment. It's often referred to as a line, but a line would go on forever in both directions, so it's not a true line. And in practical applications, there are not many real applications of a true line. So often when we refer to a line, we are talking about a line segment. The length of that line segment is equal to the distance I moved the point. This now has 1 dimension. Because our point has moved in 1 direction. Now from there, I can take that line segment and I can move it in a second direction at a right angle to the first one, and I can create If you're thinking about dragging a stick across the sand, traces out a rectangle. I can create an area. This is 2 dimensions. Two dimensions because we've moved in 2 directions. We are going to come back and talk a lot more about areas in the next couple of weeks. For tonight, we're going to come back to this idea here of moving that point in a single direction, and we're going to change it just a little bit. I'm going to take that point, start in one spot, and I'm going to go in a single direction, and I'm going to go on forever. This is what is called a ray. So a ray is defined by 2 things. One, the location of that starting point, and the direction it goes. Its direction is defined off of a grid. Think of this almost like the compass rose on a map. This is east, north, south, or west and south. Only here, what would be the east direction we define to be 0 degrees, and it wraps around. This would be 90 degrees, 180 degrees, 270, and then back to 0 would be 360. It wraps all the way around. So the direction here is going to be a really small angle, and I'm just throwing a number in here. Let's say that is 9 degrees. So this ray is going off in a 9-degree direction. So any of you go on to take technical math, or some of you, if you're in the certain programs, might take intermediate college algebra and trigonometry, you'll talk about vectors and vector directions, and that's kind of what the ray is. It's the vector has its direction that we'll talk about, same as direction of a ray, but then vectors also have an associated length where the ray goes on forever. Well, if I take that same starting point and I go in a different direction, I create a different ray, and this different ray has, of course, a different direction. Let's say that goes off at 43 degrees. Those 2 rays together can combine to make something called an angle. So an angle is simply that. It is 2 rays that have the same starting point and go in different directions. Now that starting point is called a vertex. It's just the common starting point of 1 or more rays. The angle, of course, are those 2 sides. The size of that angle is just the difference in the direction of the rays. 43 degrees minus 9 degrees is 34 degrees. So that would be a 34-degree angle. This definition of an angle was very, very popular back in the days when most people had some experience or some background in navigation. And navigation was set up on the same compass rose grid system, east of 0 and so on. Well, most people don't have that background anymore, so we've defined angles slightly differently. It works out to the same thing, but a slightly different working definition. If I'm going in a certain direction and I turn completely around to go back in that direction, how far have I turned? One complete turn is how much? How many degrees? 360 degrees, perfect. One complete turn is 360 degrees. So what if I am heading in a direction and I turn so that I am heading in exactly the opposite direction? How far have I turned? 180. How'd you figure that out? Exactly. The full turn was 360. This is just half. So what if we're going in a direction and we turn so we're going in like a perfectly square corner from where we were? That little square in the corner says that's square corner. How many degrees is that? 90. And where do we get that from? Yeah, 1/4 of the 360 or half of 180. The fourth of a full turn. And so what we've done is we've started to define angles as a fraction of a full turn. So if I construct an angle and tell you that that angle is 47 degrees, what that is saying is that angle is 47 3/60ths of a full turn. So now let's look at some other properties of that angle, those angles, some things we're going to do with them. So the angle is two rays that have that same vertex, that common vertex. Let's say we've got this angle here that is 49 degrees for this one. Now we can have a third ray starting from that same vertex going off in another direction, which is going to create several more angles. It creates this angle right here, but it also creates this bigger angle here, depending on which of the other two rays I'm using. There's also angles created over here, but we tend to only focus on the angles that are smaller than 180 degrees. But anyway, looking at these two angles here that are formed, the blue, one marked in blue and the one marked in green, this creates a situation called adjacent angles. Adjacent means next to each other or touching, beside. These adjacent angles have a property. The term is called additive. You don't need to know the word, just need to know what it means. Here, if I tell you that this angle right here is 32 degrees, this green angle then must be 49 plus 32, or 81 degrees. We can add those angles together to get the bigger angle. Again, that's only if they are adjacent. And to be adjacent, they have to share a vertex. And, of course, one of the rays has to be a side in both angles. Now, along with additive, of course, it also implies subtractive. That word's a mouthful. So let's say I have my three rays here from that common starting point or that common vertex. And I tell you that this angle here is 71 degrees. And that this angle here is 112 degrees. And I'm asking for this one. How do we find the angle in red? Subtract, exactly. 112 minus 71 equals 41 degrees. So you can see we can add and subtract angles, but again, that requirement is they must have the same vertex and be adjacent next to each other, share a side. When we have angles like that, it can be tough to know what you're referring to. Let's say that this vertex, points on any sort of plane, any geometric figure, are labeled with letters. So let's say this vertex, I'm going to call that point A. Up here, I'm going to call this B. We have point C and point D here, and point E over here. If I am trying to refer to this angle right here, if I'm trying to refer to any angle really, I name it using the symbol angle to specify that I'm naming an angle. And then I will start with a letter naming one side of the angle. So let's start with the B here. Then I will start by the next piece is going to be naming the vertex, which must be the A. And then I must name a point on the other side of the angle, which in this case would be E. So angle BAE is this one marked in red. If I wanted to describe this angle, that's angle, it could be BA. Now I have point C and D on that side there. Oops, I shouldn't have said B. I go EA. I have both points C and D on that side. I can call it either EAC or EAD. And I can switch the order if I wanted to. I could call it CAE or angle DAE. As long as I'm naming a point on one side, then the middle letter is the vertex, then I'm naming a point on the other side of the angle. Well, some special relationships here. So pretend that's the first one's a straight line and I have that extra ray coming off of it at point M. So here I have angle RMP is 142 degrees. So that'd be this angle right here is 142 degrees. Find angle PMN. How would I find angle PMN here? Don't be shy. Exactly. We know this whole thing here is 180. This qualifies as adjacent angles. So I take 180 degrees minus the 142, and I get 38 degrees for this angle. Two angles that form a straight line or alternatively add up to 180 degrees are called supplementary. So you might have guessed that we're going to be doing something that adds up to a right angle. That box again means that that's a right angle, so it has to be 90 degrees. And if I tell you that this angle here is 29 degrees, how do I find this one? Mark it in red. Perfect. Subtract from 90. 90 degrees minus 29 is 61 degrees. That's 61 degrees. Angles that add up to a right angle or alternatively add to 90 degrees are called complementary. Now, if you're anything like me when I first saw these, remembering the words was easy, but remembering which one was which was kind of tough. Well, complementary involves a right angle. And I think of it this way, you get compliments when you are right. Next relationship. Right, let's review this one a little bit. So if I put this angle right here at 51 degrees, what does this angle over here have to be? 129. How'd you get that? 180 minus 51 inches is 129 degrees. Perfect. Now, if I take this line here and extend it, and I look at this piece here, what does this angle here have to be? 51. How'd you come up with that? Okay. Now we could have done 180 minus the 129 gets us back to 51. But what you've used, what we have here is something called vertical angles. Vertical angles are formed when two lines intersect. When two lines intersect, there are several pairs of angles created. First of all, we have this pair of angles. What's the word we just learned to describe them? They make a straight line or add up to 180. They're called supplementary, right? And we have several pairs of supplementary angles. We have the 51 and the 129 there. But we would have a pair here as well, the 129 and the 51 there. These two will be supplementary, 51 and this will be 129 again. And of course, these two would be supplementary. So I've created 4 pairs of supplementary angles. Well, those are all the angles that are adjacent to each other in those intersecting lines are supplementary. We also then have pairs that are not adjacent to each other. They are across from each other. These are the ones that are called the vertical angles. They're not adjacent. There's 2 pairs of those. The 51 and the 51, and of course the 129 and the other 129. And those are always equal. And they are equal because of the supplementary pairs. 51 has to be supplementary to the 129. Well, this angle here also has to be supplementary to the 129. So it better be equal to 51 also. Questions on that? So given this information, that angle CAB equals 38 degrees, as I have it labeled. Find angle CAD, angle DAF, and angle FAB. Shouldn't take very long. You ready? So what does angle CAD have to be? 142, yes. 180 minus 32 gives us 140. 180 minus 38, I should say, gives you 142. How about DAF? 38 degrees. And FAB? 142. Good. So when two lines intersect, there really are only two angles formed. And they're just repeated. So when two lines intersect, the angles that are formed are either supplementary, like these two, as we said, or they are equal, like those two would be. Well, our next step is to take this to the next level. These lines are what we call parallel. Good. Now we're all used to most people are used to the definition of parallel lines as being lines that never intersect. And as long as we're working in two dimensions, and by two dimensions I mean on a flat piece of paper or on a flat surface, that's adequate. Parallel lines will never intersect. But when we're working in three dimensions, let's say this is a line here and this is a line there. Do they intersect? No, they will never intersect. Are they parallel? No, they're not. So a technical definition of parallel that works both in two dimensions and in three dimensions is always the same distance apart. So parallel lines are always exactly the same distance apart. The technical terminology is everywhere equidistant. We don't need to get that fancy. Whenever I have two or more lines, and then there is another line that cuts across them, it's a transversal. A transversal literally means transverse or cut across. There are now 8 angles that get formed here. This here is just an intersection of two lines. So we know that every angle is either supplementary or equal of those 4 angles. So if I give you that this one here is 127 degrees, what's this one here have to be? 53, very good. Those are supplementary, so it's 180 minus 53, or 180 minus 127 gives us 53. How about this one over here? 53, good. This one here? 127, good. Now to go to this other point over here, this other location, and we think about it, these lines are parallel. If I took this line here and slid it over, it's going to fall right on top of this line, isn't it? So it makes sense that this angle here would also be 53. Of course, once I have that one, we can just go right around the loop. This is 127, this is 53, and this is 127. Now, if this were a formal geometry class, we would have a lot of terms for the pairs of angles here. You know, when we just had two lines intersection, we had 6 pairs of angles, 4 pairs of supplementary and 2 pairs of vertical or equal angles. Well, when we have parallel lines, they've got special names like interior and exterior. Of course, interior is between the parallel lines. Exterior is outside of the parallel lines. Corresponding or on the same side of the transversal and alternate are on opposite sides. So if I said corresponding interior angles, corresponding means the same side of the transversal. Interior means between the parallel lines. So this pair could be corresponding, those two, corresponding interior. Of course, we got another pair over here that could be corresponding interior as well. What do we notice is the relationship between those two angles? They add up to 180. They're supplementary. We can have alternate interior. Alternate interior would be like this one and this one here. Also, then the other pair of alternate interior would be the 53 and the 53. What do we notice about them? Well, they're equal. 127 equals 127. Alternate interior angles are equal. There are all sorts of different names that we can come up with here. Your alternate exterior, corresponding exterior. There's something called just corresponding, which is one interior, one exterior. All sorts of different names and pairs and stuff like that. For our purposes, we don't need to know all this terminology here. So what we're going to do is just this. Just remember that when parallel lines are cut by a transversal, all of the lines formed, all 8 of the angles formed, are either equal or supplementary. 4 of them will be equal, the other 4 will be supplementary. So now along those same lines, we look at a triangle. If I form a parallel line here, parallel to this side over here, I know this angle right here and this angle right here are the same, aren't they? So if I tell you that this is 61 degrees, that one's 61 degrees. I also know that this line right here and this one angle right here, sorry, those two angles have to be the same. Let's say this is 58 degrees. Those are both be 58 degrees. Well, it's 3 angles now instead of just 2. But what do those 3 angles have to add up for there, to there? Well, it's a straight line, right? In the purple. So they add up to 180. So that's 180 minus 61 minus 58, which comes out to be 61 degrees. So this angle here is 61 degrees. What we see is all 3 angles of that triangle placed there add up to a straight line. And that is true for any triangle. The angle sum of a triangle must equal 180 degrees. So if I have, see this angle here is 128 degrees, and this angle down up here is 32 degrees. I want you to find in your notes quick that angle right there. So what's it have to be? Anybody get an answer? Well, we know the whole triangle adds up to 180 degrees. We subtract the 128 and the 32, and we are left with 20 degrees. So with what I've given you there, we'll do this. Those are parallel lines. Try that again. And we're going to have an angle here that I'm going to call 52 degrees, and an angle right here that I am going to call 61 degrees. I want you in your notes to find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 angles. So find those 18 missing angles that I have them numbered there. I'm going to give you a few minutes to do that. So let's take a peek. I kind of numbered them in a way that was, oh, come on now. All right, let's try this again. So I kind of numbered them in a way that made sense to start out. Angle number 1 down here is how big? 52 degrees. Has to be the same as that one. 2 and 3 both have to be then 128 and 128. Perfect. Now, if those are 52 and 128, are there any other angles on here that must be 52? Yeah, 17 and 15 over here are also 52 because it is this single transversal cutting these two parallel lines. So that's 52 and 52. And of course, that would make these 128 and 128. From there, it looks like there's nothing more we can do. But in the middle here, of course, we have the 61 degrees. Angle 9 over here would have to be 61 degrees because those are vertical. Angle 8 here would be 180 minus 61, or 119 degrees. So would 110. And what that allows us to find, I can either do 14 or angle 5 here. It doesn't matter which one. I have 61 and 52. 180 minus 61 minus 52 gives us that 67 degrees. So this has to be 67 degrees. That's 67. This is also 67. While we're at it, angles 14 and 12 down here are also 67 degrees. Finally, 4, 6, 11, and 13 all have to be supplementary to the 67. 180 minus 67 is 113. So those 4 angles are all 113 degrees. Okay, it is our break time. Actually, I'm going a couple minutes past, so it's 4:22. Let's come back at 4:32, and we will talk a little bit more about triangles and angles. Okay, time to get rolling again. Now, to start off our second hour, it's going to appear as though we're changing subjects a little bit, but it is going to come all back together here before we're done. I'm going to take a little bit of time to review exponents. Remember, exponents include 2 things. An exponent includes powers like this, 5 to the power of 4, which of course means 5 times 5 times 5 times 5, or 625. But an exponent also includes roots. The root is the opposite of a power. Just like adding and subtracting reverse each other, get you back to where you started, powers and roots reverse each other. If 5 to the 4th power equals 625, well then 625 to the 4th root, or the 4th root of 625, takes us back to 5. Now we are mostly going to be concerned in this course with just square roots, which means we're reversing a power of 2. If we look at some of our more awkward numbers we've worked with, things like 3/5, if I square a fraction, do you remember the shortcut for doing that? We actually can apply it to the numerator and denominator separately. What is 3 squared? 9. What is 5 squared? 25. So 3/5 squared is 9/25. Or we might have 0.3 squared. 0.3 squared is 0.3 times 0.3. How many decimal places does this have to have? 2. 3 squared is 9, so this is 0.09. If we're going the other direction, square root of 9/25, we can do just like up here, we can do the power to each the numerator and denominator separately. We can do the root to each the numerator and denominator separately. What's the square root of 9? 3, and the square root of 25 is 5. So we get right back to the 3/5. Over here, if we did the square root of 0.09, we're going to get 0.3. Just like up here, when we squared it, we had 1 decimal place times 2 gave us 2 decimal places in our answer. Here's the opposite. 2 decimal places divided by 2 gives us 1 decimal place in our answer. So it's just reversing everything. Why are square roots important to us right now? Well, we are going to continue talking about angles and triangles. And we've already talked about a special type of angle that makes a square corner like that. It's complementary if angles add up to that. It's 90 degrees, and its name is a right angle. And that terminology actually comes from what you would think, right as in correct. It is the correct angle. In construction, if you're building a house, that is the correct angle for the wall to make with the floor. It is the correct angle for the walls to make with each other at the corner. It is the right angle at 90 degrees. If we have an angle that is smaller than 90 degrees, that is referred to as acute. This one's always been easy for me to remember because cute really usually refers to things that are small. So acute angle is a small angle, smaller than 90 degrees. If we have a large angle that's bigger than 90 degrees, that is referred to as obtuse. You've probably heard the terms acute thinker or obtuse thinker. And an acute thinker is somebody that can focus in on the small details without having to look at the big picture. And obtuse would be the opposite of that. There's someone who sees the big picture without having to see all the details. So how does this fit in with triangles? Well, triangles can be classified the same way by their angles. We can have a triangle that has a right angle in it. And that would be called a right triangle. Now remember, since triangles add up to 90 degrees, that right angle would have to be the largest angle of the triangle. Because for any other angle to be bigger than 90 degrees, the total would be over 180. We can have a triangle where all the angles are smaller than 90 degrees. That is called a acute triangle. Again, it goes off of the largest angle. The largest angle in this triangle, which is probably that one, is still smaller than 90 degrees. It's still acute. And then, of course, you might have a triangle where the largest angle is larger than 90. That would be called an obtuse triangle. Well, we're going to focus in for the next little bit on right triangles, on something you probably know how to use. A right triangle, like any other triangle, has three sides. Two of those sides create the right angle. Those two sides that create the right angle are called legs. The third side that is across from the right angle, it is always the longest side, is called the hypotenuse. When I label a triangle, it is customary to label angles with large letters, capital letters. The right angle is always labeled with the capital letter C. And then the sides are labeled with small letters that correspond to the angle across from them. So this side here is across from angle A, so this would be side little a. This side here is across from angle B, so this is going to be side little b. And of course, the hypotenuse is across from the right angle, so that will always be side little c. So the two legs are always sides A and B, and the hypotenuse is side C. And of course, the rule that we're going to put out here, called the Pythagorean theorem, or sometimes called the Pythagorean rule, is of course the length of side A squared plus the length of side B squared is going to equal the length of side C squared in any right triangle. Of course, it has to be a right triangle. If we don't have that right angle in it, this will not work. Let's look at an example. Let's prove that this is true. Not say prove, but let's see an example that demonstrates this truth. Put it that way. So we have a triangle here. Let's say that this is 8 inches, 15 inches, and 17 inches. And it is a right triangle. Which two sides, well, let's do it easier. Which side would be the side C? 17. Side C is always the longest side. This is always the hypotenuse. There's always the side that is across from the right angle. Now, the other two sides, it does not matter which one is A and B, so I'm just going to throw A and B on there. So A squared plus B squared equals C squared. We'll fill in. A is 8, so 8 squared, plus B is 15, so 15 squared equals 17 squared. I probably well, we'll go with that for now. 8 squared is 64. 15 squared is 225. That adds up to 289. On the other side, 17 squared is 289. So they are equal. This is a very powerful tool. We can use this to determine, first of all, if a triangle is a right triangle. So here I have sides of 5 feet, 12 feet, and 13 feet. If I want to determine if that is a right triangle, which side has to be side C? The 13 is the longest side. That would have to be side C. So 5 and 12 would have to be A and B. It doesn't matter which is which. Now notice over here I didn't put in an equal sign here because we don't know if they're equal yet. We're just going to calculate A squared plus B squared. Then we're going to calculate C squared, and then we're going to compare to see if they are the same. So A is 12, so that's 12 squared, plus B is 5, so that'll be 5 squared. 12 squared is 144. 5 squared is 25. That adds up to 169. C is 13, so that's going to be 13 squared, which is 169. So this is a right triangle, and the right angle is between the two smaller sides. Those have to be the legs. In your notes, I want you to determine for me if this is a right triangle. This is 15 inches here, 111 inches here, and 114 inches there. I'll give you a couple minutes to figure that out. Is that a right triangle? If this were a right triangle, which side would have to be side C? The 114, the longest side. So I'd make the other two A and B. So we got 15 squared plus 111 squared. Now I can just do that on the calculator and do 15x squared plus 111x squared. I get 12,546. Then I'm going to do C, which is 114 squared, which comes out to be 12,996. Is this a right triangle? No, it is not. The next thing we can use it for is we can find missing sides. So if we know that a triangle is a right triangle, we're given the right angle, we can find the missing sides. Let's say that we were told that this is 11 feet and this here is 60 feet, and I want to find side X over here. First of all, which side is side X? A leg or a hypotenuse? It's hypotenuse, so it's going to be side C. A and B then can be either one of these. So A squared plus B squared equals C squared. We'll just fill in A is 11, so 11 squared. B is 60, so 60 squared equals C is X, so X squared. Then we do the powers. 11 squared is 121. 60 squared is 3,600 equals X squared. Next, we can add 121 to 3,600 is 3,721. What's our last step in solving this? X squared is 3,721. To get rid of the squared, we have to square root. Square root of 3,721 is 61 equals X. That's saying that hypotenuse, side X, is 61 feet. So we may have a triangle like this. This might be 13 centimeters. This might be 85 centimeters. And we're looking for side Y here. Side Y that we're looking for, is it a leg or the hypotenuse? It's a leg. So I'm going to call it side A. What's the other leg? 13. So that'll be B. That makes 85 side C, the hypotenuse. Now, the reason I made that missing side A is just because it's always easier for me if the variable is first. A is y, so this is going to be y squared, plus B is 13, so that'll be 13 squared, equals C is 85, or 85 squared is, what, 7,225, isn't it? Oops, I should just put in the 85 squared first. Get ahead of myself here. So we square it. The 85 squared is 7,225. 13 squared is 169. Then what do we have to do? Perfect. We subtract 169. So y squared equals 7,056. Very good. The last step to solve this is to square root. Y squared equals 84. Square root of 7,056 is 84. Oops, so y squared is just y equals 84, not y squared. So 84 centimeters. Okay. So let's look at some applications of this. Sam needs to repair a window on his house. On the second floor. He needs to place his ladder so that it fits underneath the window. Problem is, there is a fence built that is 8 feet away from the wall of the house. The height of the window is 14 feet. The ladder is 19 feet long. Will it fit? Well, what we're going to do is this. There's a lot of ways we can approach this problem. I'm going to approach it from what we have right here. The right triangle is the right angle is formed between the wall and the ground. If the ground's relatively flat, that should be a right angle. So that's our right triangle. The ladder, the missing ladder here, forms which side of that triangle? A leg or the hypotenuse? That is the hypotenuse, right? So we're going to call that C. The other two are going to be A and B because they're legs. Doesn't matter which is which. So we have 8 squared plus 14 squared equals C squared to find side C. Now I'm going to show you a trick to punch this in your calculator. You can do it all at once. Before you do the 8 squared plus 14 squared, you do the square root. I type in square root, and then it's 8 squared plus 14 squared. And now my calculator will do this all at once for me. I get 16.12. So C is 16.12 feet. Will that 19-foot ladder fit underneath that window? No, it's way too long. Has to be at or below 16.12 feet. Yes. Yep, we'll get to that next. So what we're going to do is we're looking at designing a sidewalk here. This is college dormitory. This here is the cafeteria. The door to our cafeteria is over here. And the sidewalks are as shown in gray there. The problem that they're having is students want to just cut across the lawn to the cafeteria, and it's destroying the grass. So they're going to come in and build a sidewalk that goes across there. Measurements are taken, and the distance from the dormitory out to the main sidewalk is 60 feet. The distance from this sidewalk over to the corner of the cafeteria is 80 feet. They want to know what is going to be the length of this longest side of the sidewalk here. First of all, is that missing length the leg or the hypotenuse? It is the hypotenuse. The right angle is right there. Our triangle, even though we've got multiple lines going in the right direction, the triangle we're interested in is formed by those three lines right there. So that being our right angle here, come on. The right angle right here, and that would be the hypotenuse. So what we have, A is going to be the 60. I'll call that A, B, and C. So 60 squared. B is going to be the 80. So 80 squared equals C squared. 60 squared is 3,600. 80 squared is 6,400. And 3,600 plus 6,400 is 100,000. That's not right. How about take away 0? No extra charge for the extra 0. How about 10,000 equals C squared? And then we have to square root. The square root of 10,000 is 100. Square root of C squared is C. So this is 100 feet. Okay, now I see why you were asking that. We are almost out of time, aren't we? Let's take a look at number 27 off the test. Number 27 is talking about a pool. It is a rectangular pool. What are the dimensions of that rectangular pool? 18 feet by 30 feet. What that means is the current perimeter of the pool is 2 times 30 plus 2 times 18, which comes out to be 96 feet. Now then, we're going to add a deck. That deck is going to go around our pool the same distance on each side. I just don't know what that distance is, so I'm going to call it X. The new length of the deck around the pool is 30 feet plus X on either end. So that is 30 plus 2X. The new width is 18 plus X on either end. So that's 18 plus 2X. So I'm going to pause there. Any questions so far? We were told the perimeter around the deck is double the perimeter around the pool. So 2 times 96 is 192 feet is the perimeter around the deck. And we're asked to find the length and width around the whole deck. So P equals 2L plus 2W. What's going to go in for P? The 192 perimeter of the deck, yep. So 2L becomes 2 times, the length is 30 plus 2x, yep. Plus 2W will become 2 times, perfect. The new width is 18 plus 2x. And now we're going to solve for x. Well, the 192 will not change here. But we do have to deal with the parentheses. We'll distribute the 2. 2 times 30 is 60. 2 times 2x is 4x. Good. 2 times 18, 36. And 2 times 2x, 4x. What's our next step going to be? Combine like terms. So the 192 doesn't change. We have 60 and 36 make 96. 4x and 4x make 8x. Any questions so far? What would be our next step? Yeah, we now start solving for x. We're going to subtract 96. 96 equals 8x. And then divide by 8. 12 equals x. Now, we can't just stop there. We have to go back and answer the question. 12 equals x. That means this is 12 feet. This is also 12 feet, right? The width is 18 plus 2 times 12, or 18 plus 24, which is 42 feet. The length is 30 plus 2 times 12, or 30 plus 24, which is 54 feet. So the new dimensions are 54 by 42. You bet. Does it just ask the width of the deck? I thought it asked for the length and the width after the deck. Okay. If you just had 12 on there, I would take it. Okay, so there is a new quiz that is due tomorrow, Wednesday at 11:59 p.m. And then, of course, the new homework that is due for next Tuesday, next class. With that, you guys have a happy Thanksgiving. Enjoy your long weekend, and we'll see you next week.